Hello everybody, welcome back to a session of calculus. Today we will be talking about linear approximation or linearization as some books might actually put it. So here's the idea behind the linear approximation here. Let's say that again, we have a curve and we have an equation, and it could be something very, very complex, unfortunately. What we can do as of right now is solve for the equation of the tangent line at any single point. So for example, if I go to the curve and I go to any point right there, I can definitely solve for the equation of the tangent line by solving for its derivative, and then afterwards, getting the line, and that's pretty much it. Now, if you notice, and as we mentioned a while back, is that something we mentioned a while back is that whenever you look at the curve and also the tangent line locally, that is to say, if we look at it within like a small little window over here, you'll notice the two are basically almost identical to each other, or there's not that much of a difference. So what that means is that, hey, sometimes it might be nicer to use the equation of a tangent line rather than the equation of the curve if we were to look at things locally. And I will go ahead and give you an example of that. And that's basically the idea of local linearization, or in this case, linearization just for short. Okay, so here's an example of what I'm talking about. Let's say that I asked you to estimate what is the cube root of 27.1. Now, if you're thinking, okay, well, I know how to take the cube root of 27 because that's equal to 3, that's basically what we have to work with, and that's pretty much all we need. So here is what we're going to do then, okay? I know for a fact, and let me go ahead and write this down right now. The cube root of 27 is equal to 3, which is nice then. So I'm going to go ahead and say let my equation y equal to x to the power of 1/3, which is basically equivalent to this equation right here. And what I'm going to do is I'm going to find the equation of the tangent line, okay? Find the equation of the tangent line at x equals to 27. So in a way, what I'm doing is I'm basically setting up this scenario over here where I have the equation of the curve, and I'm going to find the tangent line so then I can use the tangent to estimate what I'm actually going to solve for. So going back to this, let's go ahead and go through the procedure as we normally would. Let's see. So if y is equal to x to the power of 1/3, then that means that y prime is equal to 1/3 multiplied by x to the power of -2/3. I'm going to go ahead and substitute x equals to 27 in order to find the slope of the tangent. So y prime in this case is equal to 1/3 multiplied by 27 raised to the power of -2/3. So having to do this without a calculator, let's see, we can go ahead and write 27 as 3 to the third. Maybe that might be a little bit nicer to look at. Then we have -2/3 on the outside. You can see that the 3 and the 3 over here cancels each other out. So what we have now is 1/3 multiplied by 3 to the -half, or -2, and that gives me a slope of 1/27. So my equation of the tangent line then, so the equation of a tangent is going to be the following. Okay, so specifically again, equation of tangent at x equals to 27. So that's y minus is equal to 1/27 times x minus 27. Now, what is the y value that's there? Well, I'm going to go ahead and solve for it by taking this right here and plugging it into my equation. So y is equal to 27 to the power of 1/3, which we said we know how to solve for. That's going to be equal to 3. So there it is. That's going to be my tangent then. Now, remember, the idea here is to estimate what is this thing right here. What is the cube root of 27.1? And if you remember what I just said over here, right? Locally, the tangent and the curve, are going to be so close to each other that we can just go ahead and use one equation over the other because of its simplicity. So going back to what I'm going to do over here, I'm basically going to plug in x is equal to 27.1 into my tangent equation, because that's a lot easier to plug in and solve what y is rather than trying to figure this out without having a calculator. You got to remember that back when they created calculus, there was no such thing as a graphing calculator. So they have to basically use what was available. And that's what's happening in this case. So here we go. Y is equal to 3 plus 1 over 27 multiplied by x minus 21, x which is equal to 27.1. So let me go ahead and make a small little adjustment right there. So plug in 27.1 minus 27. And this right here, that's going to be my approximation for my answer then. So you can see how the 3 is definitely a part of the answer. And then plus whatever this residual is, that's going to be the amount that you have to increase in order to get to that approximation. So 1 over 27 multiplied by 0.1. So that is going to be equal to 3 plus 1 over, I guess we can write it as 1 over 270 then. Okay, so that is going to be our answer. Now, let's see. In terms of like how does that compare to my actual answer, maybe we can put it into calculator and figure that out. We have, let's see, 3 plus 1 over 270. I'm putting the in the calculator on the side. That is approximately equal to 3.0037. Okay, but whereas if I take the cube root of 27.1 raised to the power of 1/3, that right here, if I were to take it and put it into the calculator, that numerical value is approximately around 3.0037. So it looks like it's pretty close, almost identical in a sense then. Okay. All right. So now let's go ahead and, like say, hey, this time around, I want to estimate what is the cube root of 26.7. So I'm basically just kind of using the same setup because the same, the beginning part is pretty much the same. You're just solving for the equation of the tangent line. But what if I want to go backward instead of forward then? Well, it's still the same thing. You're still going to take your equation of the tangent line, which is y minus 3 is equal to 1 over 27 multiplied by x minus 27. That's my local linearization equation, or tangent equation if you just want to be, if you want it to be short. Plugging in now, x is equal to 26.7 because 27, that's where the perfect cube root is, and that's where I want to take the tangent. So plugging that into equation, we have now y is equal to 3, and then plus 1 over 27 times 26.7 minus 27. And if you notice, what you're going to get this time is that you're going to get a negative number. So it's going to be 1 over 27 multiplied by, looks like it's going to be negative 0.4. So my round off is going to be 3 minus, let's see, it's going to be 4 over 270 then. So that's going to be my approximation in this case. Okay. So hopefully, that's pretty straightforward as to like what's the point of using the tangent, because, we know how to solve for the tangent now, but, it would be nice if we can kind of apply it to some of this stuff that we've been learning all this time. Just one small thing before I move on though. For this method of local linearization, it's probably not ideal if you want to solve for maybe something like, say, the cube root of 21, or maybe like, say, the cube root of 19. The reason for that is notice how far 21 and 19 are away from 27, right? If you go back to my generic picture of the tangent line and the curve locally, if you go further and further away, right, you'll notice that there's going to be more and more error then as a result, because the two are not going to be the same. It's going to be the error between the y values on the tangent and the curve. It's going to get bigger and bigger away as you go further and further away from that local linearization. Okay. All right, so now let's go ahead and look at this last example over here. And this is basically going to talk about that error that we were saying. Given that y is equal to x to the power of 1.5, what I want to do is at x equals to 1, if the values of delta x, the change in x on the curve of y is equal to x to the power of 1.5, and dx, which is the change in x on the tangent line, what are the values equal to? Are equal to 0.5. Okay, so delta x and dx are equal to 0.5. Then I want to know what are the values of delta y and dy. Okay, so here's what I'm saying. Here's what I'm saying for this problem. You can see on this curve over here on the right hand side that the blue is going to be the graph. Y is equal to x to the 1.5. Now, what I did was I went ahead and did all the quick work for you, which was to solve for the equation of the tangent line at x equals to 1. So that's going to be the green curve that you see over here. So you can see also the point of tangency, which is going to be 1, 1, 1. Now, here we basically said, okay, I want to use this linearization, or this equation of the tangent line, to estimate certain values. In this scenario, what I'm telling you is that the change of x is going to be equal to 0.5 for both cases. So here in this picture, if you can kind of visualize it, I'm going to try to draw it for you right here. This right here, the change of x, which we denote as dx, and also delta x, right? Now keep in mind, remember, delta x right here means the change of x on the curve, okay? So delta x is the change of x that's on the curve, whereas dx is going to be the change of x on the tangent line. So that's going to be delta x and that's going to be dx, and they're both going to be the same in this scenario, which is going to be equal to 0.5. Now, I'm going to go ahead and create a triangle, a right triangle, because that's where you normally see delta x and dx and so forth, and also dy and delta y. So here's what that means. I'm going to move over by 0.5 for both of the equations. This part right here, this portion that goes from this point over here to the very top of the curve, that is going to be my delta. That is going to be my delta y. Okay, that's my change in y on the curve. Whereas from the bottom over here all the way to where the tangent is, that is going to be dx, because remember, dy dx means derivative, so that's why you're using the tangent curve, whereas delta y delta x is going to be in reference to the original equation because it's the change of y over the change in x. So I want to know, hey, if you move over by 0.5, how much of a difference is there going to be in the y value then? Well, now that you can see what I'm asking for graphically, then maybe you can actually solve for this then. In order to solve for dx, I think what I need to do is I need to take the equation of the tangent and plug in 1.5 in this case, right? So here, let me go ahead and write that on the side. So y minus 1 is equal to 1.5 times x minus 1, right? So that's the equation of the tangent. And since delta x is equal to, so delta x is equal to dx, which is equal to 0.5, then that means I'm moving 0.5 units away to the right. So that means my x value is going to be 1.5 then, because 1 plus 0.5 is 1.5. And then plug everything in. So y, in this case, is going to be equal to 1 plus 1.5 multiplied by 0.5. Maybe we write it in the fraction just so that it's a little bit nicer. So 1 plus 3 over 2 multiplied by 1/2. So the answer looks like it's going to be 1 plus 3/4. So then that means that according to the if you were to plug in 1.5 into the tangent line, the y value is going to be 1.75. Now I'm going to go ahead and do the same to solve for what is the change in y. Well, the change in y, since delta x is equal to dx, which is equal to 0.5, right? If you notice then on the original curve, y is equal to x to the 1.5. I'm going to go ahead and plug in 1.5 in this case. So 1.5 raised to the power of 1.5. So I'm going to throw that into the calculator, okay, just to see what I get. So 1.5 raised to the power of 1.5, and that is going to be equal to approximately 1.831. So that's the actual y value that's over here. Okay, so that's going to be 1.5 comma 1.831 or 837. Whereas if you were to use the tangent right there, that's going to be 1.5 comma 1.75 then. And the last thing is, well, what does the absolute value of the difference between those two answers is going to give you? Well, if you look at the graph, if you take the difference between the two, that is going to represent the error of using this local linearization according to this value of x. Okay, so it tells you how much of an error that you actually have. And if you make that triangle, that right triangle smaller, because it's more and closer to the value of x is equal to 1, then you can see that the error is going to be smaller and smaller too, because your tangent line is going to be so much closer to the curve in that case. All right, thank you so much for watching. I will see you next time. Have a good one. Stay safe.